In Chapter 3, the checkpoint near the end of the chapter is about adding and subtracting fractions. So while you did a lot of this work last year and in 4th grade, I want to make sure that everybody understands how addition and subtraction of fractions works. So first of all, we're going to take a look at the simplest type of adding and subtracting problems with fractions, and that's where the fractions have the same denominator, like in the case of 1/4 plus 2/4. Now I'm just going to model this problem off to the side really quick. So we might have 1/4 of this circle and we want to add 2/4 onto it. If we do that, we can see that what we end up with here is 3/4. So that's pretty straightforward. The thing to watch out for is that sometimes I'll see people who add these denominators together. But if you can think about a model like this, you understand why it makes sense only to add those numerators. Subtraction is the same idea. So let's say we wanted to take 4/5 minus 1/5. So we would start off with 4/5 of our circle filled up over here. And one of the ways to think about subtracting 1/5 is to just take one of these pieces away, and we can see that we're left with 3 out of the 5 pieces needed to make a whole. So the difference between those two is 3/5. Okay, so when you're adding or subtracting fractions with the same denominator, we want to make sure we're just adding or subtracting the numerators, keeping that denominator the same in our answer. Things get a little bit more interesting when the two fractions have different denominators. So think about the problem 2/3 plus 1/4. I could model this out by starting with 2/3 and then adding 1/4 onto it, but the problem is it's a little bit hard to figure out what that resulting fraction is. It's not thirds, it's not fourths, it must be something else. So keep in mind we can use the giant 1 to rewrite fractions so that their denominators are the same. So I could take 2/3, for example, and multiply it by some sort of a giant 1 to get a new form of that fraction. And I could do the same thing with 1/4. I could take 1/4 times some giant 1 and get a new way to write that fraction as well. Before I do that, though, I have to figure out what giant 1 I want to multiply each one of those by. Now keep in mind that whatever I end up with over here has to be a multiple of 3. And whatever I end up with over here has to be a multiple of 4. So what I want to have here is a common multiple of 3 and 4. Now you might already know what a common multiple of those two numbers is, but if you're not sure, you could use a listing strategy to find that. So I'm going to list multiples of 3 here, 3, 6, 9, 12, 15. I could keep that list going if I need to. And I'm going to list multiples of 4, 4, 8, 12, 16, 20. But oh, wait a minute. Here I've got 12 as the least common multiple of both of these. Now you don't have to use the least common multiple, but if you do, it keeps your numbers and your fractions a little bit smaller and easier to work with. So I want to change both of these fractions so they're written as 12ths. Now I know that 3 times 4 equals 12, and to make this a giant 1 I have to put 4 in the numerator over here. 2 times 4 gives me 8, so 2/3 is equal to 8/12. Down here I'm going to be thinking 4 times what gives me 12? That's 3. 1 times 3 in the numerator is going to give me 3/12. So I can go back to my original problem now and say that 2/3 plus 1/4 is mathematically the same as taking 8/12 plus 3/12. And I could also illustrate that over here. If I was to pull in some 12ths pieces, I see that it takes 3 of these 12ths pieces, 1, 2, 3, to make 1/4. And for each one of my thirds, it's going to take 4 of these to make 1/3. So there's 1, 2, 3, 4 12ths. I can replace 1/3 with 4 12ths. And I can replace my other third with another 4 12ths here. Okay, another 4 12ths. And putting all these together is basically going to be the same problem. It's the same problem, just written differently. So here I have 4 12ths. Here I have another 4 12ths. So I'm taking 8 12ths plus 3 12ths. And my total then, if I go back to the method we talked about earlier, is just going to be 11 12ths. Adding those numerators together, keeping that same denominator. Okay, let's take a look at one example of a subtraction problem with different denominators. So my problem is 2/3 minus 1/6, and I'm going to model that out by starting with 2/3 over here, and this is the amount that I want to take off of that. But the problem is these pieces are too big. I can either take this much off or take nothing off. So again, I want to find a common denominator for these two fractions. So I'm going to think about multiples of 3 and multiples of 6. Here are my multiples of 3, 3, 6, 9, and so on. My multiples of 6 are 6, 12, 18, and so on. But take a look at this. I really didn't need to go that far because 6 is a common multiple of both. So if I think about my fractions, I'm going to take 2/3 and multiply that by the giant 1. That gets me to 6ths, and I know that 3 times 2 equals 6, so I'll be taking 2 times 2 to change that into 4/6. Now look at the fraction 1/6. I really don't have to do anything with that because it's already written in sixths. So I can come back up here and rewrite my problem as 4/6 minus 1/6, and the answer is 3/6. Okay? Now, if we go back to our model again, remember that what I want to do here is change this so that I have that common denominator. So each 1/3 is equal to 2 of these sixths. Okay, so I put these down here. If we take 1/6 away from this, what we're left with is 3/6. 1, 2, 3, 6. Of course, you might also notice that that fraction is equal to the fraction 1/2. So I can simplify this answer in the end down to 1/2. Okay. Today, as you work on your addition and subtraction problems with fractions, it might be helpful to go back and review portions of this video. Another great resource is if you go into your toolkit, that's again this book right here, and look at page 29, there's a nice math note section on adding and subtracting fractions. They show this just a little differently than I did here, but it's the same idea of using that giant 1 to find a common denominator. All right, thanks.